Hi Liz, I hope this is helpful. There's quite a lot going on in that question, I must admit. So, big ideas here are that when you have an exponential growth or decay, when you take logarithms of this, you end up with a straight line relationship. So, my understanding of this is that if I did an experiment and I purely counted the number of bacteria per time, I would get plots like this. And it would be quite hard to prove or fit an exponential curve to that. I certainly wouldn't be confident drawing a curved line of best fit and then approximating the actual relationship. However, a straight line is much, much easier to do. So that's why scientists, well, correct me if I'm wrong, but that's why scientists tend to take logarithmic values because of this relationship. If you can show that something is a linear relationship, when you have your control variable and your response is logarithmic, it must be exponential. And I'll just do a very quick proof why. You can choose any base of log, but your logarithm in the question is base 10. So I'm going to take log of both sides. Sorry, my Apple Pencil is a little bit laggy. There we go. And using some laws of logarithms, we can show that this makes a straight line relationship. So the left hand side is just going to stay the same. I can't really do anything with that. But if I've got two terms that I'm taking the log of that are multiplied, I can write that as an addition. And if you're doing this with A-level students, if they've done maths, they will have done that in year 12. Okay. It's really bad, my Apple Pencil. There we go. Another law of logarithm is if we've got this power, I can bring this down as a multiple. And again, they'll know that. But what that's helped me to do is it doesn't matter what values I've got of k and a in the original equation. I'm always going to be able to take these steps, and a bit of GCSE maths again that all of the Latimer students will have done is they should now be able to recognise that this has got the same property as a straight line graph. So let me just persevere with my Apple Pencil. Any straight line has got y equals, and I'm going to write it in the right order so it matches, mx plus c. Okay, now I know that we would usually write it as mx plus c, but this here is your constant value because this is fixed. This isn't a variable. The only variables you're using are the number of something and the time. So this is going to be constant, and that's going to be the equivalent of the y-intercept on your graph. So we're going to be able to equate those two things, find that value, which is going to be helpful in solving your problem. The x variable is time. So that means that this m is equivalent, the gradient of this graph is equivalent to log base 10 of a. So we're going to be able to form two equations, find those values, and then substitute them in and solve the problem for when it's 10 hours. So the first one I'm going to do is I can see really quickly that my y-intercept there, if I zoom in, I think, 5.6. Okay? So when I do that, I'm going to, God, it's really bad. 5.6 is equal to log base 10 k. Okay, and just doing the inverse of that, raising that up to a power of 10 is going to help me find what that k is. Now that gives me a very strange answer, but I think your question, it's going to round to like nearest significant figures to give you the 4 that your solution is. Let me just type that in. So you get 398,107 point something. Okay. That's that value of k that we're going to get in front, so we can put that in our formula. The other thing, we've got to do a little bit of work, but we can find the gradient, and I'm going to pick 2 simple points, so there's no kind of like error that creeps in. I'm going to pick that one, because that's obviously the 5.6, and then I'm going to pick that one, because that goes straight through a point, so that's 7.1, 2, 4, 5, 6. Encourage your students to do that, because that's going to minimize the error in their gradient. So then that means that the change in y is 2, and I've gone from 0 to 600. Whoops. So from 0 to 600, there we go. And that's going to be equal to log base 10 of a. Doing the same method that we just did with the k, I can raise that up as a power of 10. So I get 10 to this power. And I think what I'm going to do is that's going to give me quite a small, or it's going to give me a number that's only just slightly bigger than 1. So to not lose any accuracy, I'm going to leave it like that. Right, let's have a look then. So let's put this k in the a back to the original equation. So n, the number of bacteria, is equal to this very, very odd number. IT need to give me a new Apple Pencil, I think. This one's on its last legs. And then we're going to times that by a, so because it's k times a in our formula. 600. And then raise it to the power of t. Now, it's said in the question that it was 10 hours. So that means that my time, because we're measuring it in minutes, is going to be 600. And actually, the question has been quite nice now, because if I have that power of t, it's going to cancel with that dividing by 600. So what I end up having is this value. So copy, paste. That was better. Times by 10. Which actually is the solution that we want at the end, because it will give us, if we round it, it will give us 4 times 10 to the 7. Okay, I hope that was helpful. I have actually got a few other questions like this, but that's the general idea. You could give any student a straight line graph with a logarithmic y, and that method will work every single time. You could actually, for biology, you could give them that formula and say, do this bit with the gradient, do this bit for your y-intercept, put the values in that, and it will chuck out the answer. Okay, so I hope that's helpful. If you want to chat any more about it, that's fine, and I'll have a look at the Google form tomorrow. All right, take care, bye.